Okay, in this podcast we're going to talk about the trends for properties, physical, chemical, in the periodic table that go beyond things like electron affinity and ionization energy, but are related to that. Okay, so the best way to talk about trends on the periodic table, property trends, is to talk about how the periodic table is broken down into, you can think about it as three sections. The far majority of the elements, more than 80% of them, are metals, and they are on the left-hand side of the periodic table. On the right-hand side, we have nonmetals, and this stair step in between are known as the metalloids. Okay. In general, the metals on the left-hand side are lustrous, just a fancy word for glossy, malleable, which means you can hammer them into a sheet, you can form them. Ductile means you can draw them into a wire. And they are good conductors of heat and electricity. And of course, they tend to form positive ions because they have a low ionization energy, right? They have a low ionization energy. It's easy to remove their outer electrons, doesn't take much energy, okay, because they have all that shielding from the inner core electrons, okay. Nonmetals, on the other hand, right-hand side of the periodic table, they're going to have many electrons in their valence shell. They are going to therefore form, this should say, negative ions. They tend to be dull, brittle. They are poor conductors of heat and electricity. And they run the gamut. While metals are almost all solid, except mercury, which is a liquid at room temperature, the nonmetals are a mix. A lot of them are gases. There are some solids, and bromine is a liquid. Okay. They form negative ions because they have a very high electron affinity. They want another electron. They are more stable with it. They release a tremendous amount of energy when they get that additional electron. Okay, so metalloids are in between the metals and the nonmetals. They have some characteristics of metals and some of nonmetals. Here we see silicon, which is shiny, but it's brittle, and it's a pretty poor conductor. Now you might say, why are we calling it a poor conductor? Because isn't Silicon Valley built around this idea that silicon is a tremendous boon to the electronic industry, which relies on electricity? So let's talk a little bit about what a semiconductor is. And in order to do that, we first have to talk about what a conductor and an insulator or a non-conductor is. All right, so let's first talk about conductivity. Conductivity means I have an object that allows current to flow, electricity to flow, right? So what is electricity? Well, it's the flow of electrons, okay? So if I have an object and I put some negative source next to it and a current flows through it, the electrons are shifting towards either the neutral, which becomes the negative side, or I can put something positive against an object, and still the electrons are going to flow towards the positive. Okay, so that's what electricity is. So let's take a look. All right, so here's a conductor. If I have an object and I bring something positive towards it, the electrons are going to come towards it. When you move the positive object away, they're going to go back. Same thing, take negative next to it, move it near it. It's going to cause the electrons to flow, the negative or the electrons. If I have an insulator, what happens is the electrons move, but they stay within their atom. They don't move further than their own a particular radius. Okay? So in both cases, electrons are moving. But in the case of a conductor, those electrons will move right away from their own atom. Okay? So one of the things that makes metals so conductive is that, first of all, they have just a couple of valence electrons, one or two or more, and those electrons are not localized to their own specific atoms. They are free to move. Sometimes it's known as a sea of electrons. Those electrons can jump between atoms. They are shared. They are all attracted to the various nuclei of the element, but they're able to move. Okay? An insulator, on the other hand, does not have those valence electrons that are free to move. So when something negative comes next to it, the electrons can move within the atom, get shifted towards or away from the source, but they cannot jump to another atom. Okay. Okay, if you, so let's talk about semiconductors. There is a section in the book, 12.3, that talks about semiconductors, although I think the treatment in our book is weak. There's lots of resources you can find online for semiconductors. You don't need to know all about semiconductors. I mean, you could take a whole course on semiconductors. But I'll tell you the essential things you need to know. So most semiconductors have 4 valence electrons. They're part of the carbon group, right? And just like carbon will form sheets of carbon, silicon does the same thing. It forms basically covalent bonds with itself, so that you end up with this sheet-like structure where everybody has an octet because of the nature of the bonding. In general, silicon, when it's just plain old silicon, does not conduct electricity. You can, with heat, cause an electron to get ejected, and that would cause basically what they call a hole that is positively charged, and that positive charge can jump around and cause some conductivity. But more typically, what happens in the electronics industry with things like silicon is they use doping. And what doping involves is either adding something like, let's say, boron, which is going to have 1 less valence electron. It's going to have 3 valence electrons, or something like phosphorus that has an extra valence electrons. That's going to cause that extra electron to shift, or that electron from silicon to shift in the case of boron, causing a shift in electrons. Okay? And what this does, it's pretty complicated, but let me just tell you some of the advantages of what a semiconductor can do, is it allows basically what's called switching, where you can have the electricity flow until it hits a junction, and based on what's there, depending on what it's doped with, or how much it's doped with, it can make a decision about whether the electricity is going to shift and go that way, or shift and go that way, or shift and go that way. So you can make decision trees within a circuit that are very advantageous for electronics. So that's really all you need to know about semiconductors. Silicon is the most common one. There are others. They all have 4 valence electrons, pretty non-conductive until they get doped. That doping spurs movement, shifting of that electron, and that electron movement can be tailored to what is needed for the electronics. Okay. We say that as we go left on the periodic table, we have increasing metal character, both left and down. So basically, the easiest it is to take off an electron, the lowest ionization energy, is characteristic of metals. And the more metallic has the lowest ionization energy. Very easy to pull off an electron to make a positive ion. Okay, so it's down in this corner, increasing metallic character. Okay, so if we look at metals, they tend to form cations, right? They have just a couple of valence electrons. They're going to lose those valence electrons. They have very low ionization energy, and they are going to form cations, or positive ions, as opposed to the nonmetals, which are going to form negative ions. They have high electron affinity, They gain electrons, not the noble gases, right, which would tend to be exothermic electron affinity, but these guys want to take on an electron. It's more favorable, they're more stable, they're going to form anions or negative ions. All right, so let's see if we can predict for metals, we're talking about the yellow now, across a period and down a group, what the reactivity is going to be. Are the metals, first think about it across a period, are the metals towards the left or towards the right going to be the most reactive? And down a group, top or bottom, and why? Give it some thought and then come back. Okay, so let's take a look. If I period, my reactivity is going to go down. Okay, so as I go across, the reactivity goes down. And that's because as I go across, I am adding another proton in the nucleus. I'm not causing any more shielding. So those electrons, as I add them, are going to be more and more tightly held. So I'm increasing my Zeph. Those electrons have stronger Coulombic attractions, making the ionization energy go up, making it more and more difficult to attract an electron. Okay, as I go down a group, what happens is if I start with, let's say, lithium, and I compare that to potassium or rubidium or cesium, that electron is further away from the nucleus, has lower Coulombic attractions, less attracted, therefore much easier to remove. So the most reactive metals down here in the corner. How about nonmetals? Okay, so I didn't give you a chance to predict, but I bet you could have. And if I go across a period, now I've got to say, let's exclude the noble gases, but in general, as I go across the period into the halogens, I am increasing my nuclear charge, I'm increasing my Zeph, my shielding is not changing, I have stronger Coulombic attractions, which means adding an electron is easier. They have stronger electron affinity. Okay? If I go down a group, my reactivity is going to go down. Because again, as I think about what I have here I have, let's say this is the nucleus, here I have fluorine and chlorine and bromine and iodide. Nonmetals are reactive because they add an electron. This atom out here is less likely to add an electron because electrons get added because of the positive pull of the nucleus. Okay? All right. Groups. Right, so alkali metals tend to be soft. You can cut them with a butter knife. They are low in density and low in melting point compared to other metals, okay? You only find them in compounds because they are so reactive, they are going to react with other stuff around them. They are the most reactive group of metals, more so than the groups next to them or the transition metals. So the most reactive is down here at the very bottom. Alkaline earth metals, which is group 2, and they're going to, of course, form +2 charges because they're going to lose those 2 valence electrons, are a little bit higher in density than group 1, a little bit higher in melting point, but less than the transition metals. They are still so reactive that you only find them in compounds. They're not going to be found naturally in matter. And they are very reactive, but less than group 1. So most reactive, second most reactive. Oxygen group is a mixed bag of elements. This is group 16, sometimes called 6A. If you think about it, oxygen, sulfur, and selenium are nonmetals. Tellurium is a metalloid. Polonium is a radioactive metal, so it's really a mixed bag. Oxygen is interesting in that it has 2 allotropes, and an allotrope means that it's got 2 different forms, 2 different arrangements of atoms that it will naturally occur in. The most common that we're familiar with is oxygen, O2. It's a diatomic molecule. But ozone is also another allotrope of oxygen. It is O3, And it's an interesting structure in that it's got one single bond and one double bond. But yet, that's a resonance structure. We'll talk more about resonance structure when we get to the bonding unit. Okay. Sulfur is also an interesting element in that while we talk about most elements exist as single atoms, or we have those 7 diatomics that exist as, let's say, O2 or N2 or H2, sulfur's most common and most stable allotrope is S8. So it's actually kind of a crown-like, ring-like structure. All right, so on the right-hand side now, the next column is going to be the halogens, which is going to be your most reactive nonmetal, again, because they have very high electron affinity. They have low density and low melting point. In fact, their melting point is so low that these three, the first three, are going to be gases at room temperature. Okay, iodine's going to be liquid and acetine's going to be a solid. And you can see that here. If you look at the elements, fluorine is a pale yellow gas, chlorine is a green gas, bromine is a liquid at room temperature, kind of brownish, iodine is a solid, and it's a light purple, and acetine is a dark purple color. So interesting. The colors really vary. States of matter really vary. But they are the most reactive metals. And of course, like we said, fluorine is going to be the most reactive metal because its nucleus is most exposed, making it want to attract an electron. And the last group we'll talk about are the noble gases. They have astronomically high ionization energy, which means very, very, very difficult to remove an electron from them. They have a stable octet. They also have a positive electron affinity. Remember, electron affinities are only positive when you have to force that atom to become less stable by taking an electron. So we say that their most typical property is that they're unreactive. Now, in fact, there are a few compounds that can be made from noble gases, but that's the exception, and we'll talk about those when we get to bonding. They are all monatomic gases. Okay? All right, so that's going to do it for us.